Good morning, everyone. While we are starting to talk about the panel, I would like to invite my panelists to be with me here. So while they are getting to the stage, I want to ask the audience a few questions as we started to be engaged more. So, how many of you are considered starting the digital twin journey, or um, just by raising your hand, I'm curious about if you're considering it or you're in the process of doing a digital twin journey already. Okay. Okay, well, that's great. That's a 20, 30%. Um, how about this something new you just want to learn more about what's going on? Curious how many people are in that category. I didn't see anyone. So that means the remaining 60% is already the pro, or you already completed the digital twin journey. We'll have some hard questions then. Um, all right, I got all my panelists here. So after we talk about all the work group progress and things, and personally, I think this is a great group. And I remember 3 years ago we starting the work group, and personally, it really helped me to facilitate a lot of a digital twin and digital transformation discussion within the utility. I mean, with the clean water services. So I'm really excited with the panelists today. The topic is going to be a continuous journey. I think that's the key. We're all utilizing automation, SCADA, IT systems, S3 platform, Autodesk, and things. But how do we evolve over the years to become more of systematic approach? We'll talk about more. Our panelists are representing a global perspective, and also they will talk both from a small and a large utility perspective and the use cases and lesson learned. What we'll do is we'll have each speaker to introduce themselves, and then they will have about 6 to 7 minutes to go through the presentation. We'll hold the questions at the end, so we'll have a more of an engaged presentation, the discussion afterwards. Um, all right, with that, we'll start with Patrick.
So I'm Patrick Bonk. I'm a global product marketing manager for our ops analytics and AI solutions. I'm with Javier Cantu, who's a solutions engineer for our ops analytics and AI applications. Um, okay, so our topic for today is components, challenges, and continuity with higher order digital twin maturity. And when giving thought on how best to articulate the progression of where you are now on your digital twin journey, we considered the multiple SWAN digital twin framework. So whether it was architecture, the life cycle, the outcomes, the maturity of the models you're using, the common framework for describing your place in the digital twin journey is the digital twin maturity framework. So this indicates the level of sophistications with the model you're using. So on the far right side, you have prescriptive analytics, and that's what should happen with your asset. So that's an optimal recommendation given by the AI, and this tends to be quite aspirational for many people. So the maturity framework, it's often represented as steps. Like it's this way. It's always like a step-to-step thing. It's always aspirational. It always seems really far off. So we wanted to flatten it here to communicate the continuity between the types of analytics types. And then depending on the use case, the data available and the sophistication of your instruments, you can determine where you are within that framework. So a brief run through today looks at the components and challenges and the continuity between those types. Okay, so why prescriptive analytics, and why are we aspiring to use them from the beginning? Well, essentially, AI helps the plant operators take a uniform approach for optimum plant operations to the always changing conditions we're dealing with. So for this particular figure, the outside lines represent your process constraints. The orange circle is your operator's comfortable region of operation. The green circle is where the AI is advised in the operating range. The top right is the most economic operating point. And then each operator has a different skill, experience, and way of operating the plant that they need to deal with. So one of the main challenges when aspiring to progress to higher maturity levels with digital twins is the natural and perceived complexity of the problems we're solving. So the human challenge is we're just not ready. So the human side is that fear, that doubt, that uncertainty into taking something new. And then you have the technical challenges where, the belief is our system isn't sophisticated enough. We don't have enough data and the subject matter expertise to get started. So that just naturally there's a general perception around, AI is a black box and we're not going to understand what the outputs are to help us inform our decision making. And then there's just natural technical challenges. Plants, networks, they're actually really complex. These problems are really hard. And then subject matter expertise is actually required for incorporating system limits and process knowledge into this process. So in general, the AI can abstract out any process schematic, whether it's water, wastewater networks, and treatment plants, into a real-time predictive model that accounts for changes in various operating. Yet it often inhibits the first step to optimization. So Javier is quickly going to go through the components of the system.
So mainly what I want to cover is like where this could be applicable. And I'm going to go through like one of our implementations and one of the case studies where we learned a lot through the process. As he had mentioned, this does fit a whole bunch of different use cases within a utility, which kind of drives to what some of the answers that were coming in. How do you create a business case? You find a good outcome, something, a specific target. And particularly for us, we had a customer in South America. It was actually a paper mill. So it was on their wastewater treatment side. Talking a little bit about breaking down to some of the biggest challenges associated with this, I say it's upstream of the digital twin. We've got a lot of numerical knowledge of our systems, our processes, maybe decades, sometimes centuries old when it comes to like activated sludge or anything of the sort. Bringing machine learning on top of that can help guide some data gaps. Data gaps, I would say, are usually the biggest trouble when it comes to any sort of application of machine learning. In this particular case study, the desired outcome was to essentially improve sludge quality because we were looking for ways to reduce the amount of oil use for a cogeneration facility on site. Sludge was being fed to their cogenerating facility as fuel in order to reduce the amount of oil that was being bought inside the facility to run the steam plant. Biggest challenges were, getting consistent data streams. Sometimes sensors don't work. I think everyone's gotten there, and everyone's reached a point where you get that flat line, or maybe it's just a big data like gap, right, in your historical analysis. In this particular study, what we did, we had to grab like 4 or 5 years worth of data, and we supplemented the data set with numerical analyses. What we found the best use in this particular case was to kind of create a clustering approach using machine learning techniques where we could actually bring in correlations on production data from the facility. QA and QC data in commercial applications or production data is a lot more full. There's more of a complete data set than there is usually in their ancillary facilities like water utilities or wastewater utilities. So being able to create an environment where we could actually forecast and determine loading rates based off the demand of the market and what the facility was trying to produce in paper, we were able to develop strategies on how to approach very specific sludge data sets throughout the year's demands changes. That resulted in very marginal reduction in polymer use, but ultimately much drier cake. And that drier cake led to better fuel consumption, more steam production, and a lot less oil being ordered for the ultimate cogeneration facility. So this was a clear case where you can find a business case study to kind of approach digital twin as a whole, and kind of expand slowly throughout.
So to bring this all together, we're establishing a digital platform where it accommodates multiple model types. And a way to further align the core concepts of a digital twin is to contemplate the time horizon you're solving your problem. And alluding to what Andy spoke of earlier in terms of making more value from the hindcast data, our forecast data, this is a way in which we're accommodating for that. So if you look at the past, you're actually using that to inform your network and system performance using user-built workspaces and performance KPI metrics. If you look at your present moment, it's used to generate alerts based on incidents occurring in your system. And then from there, our beloved models can generate the what-if scenarios for things like contingency responses, and it'll give you visibility where you don't have sensors. And then the future, that's where we have future set points generated from the AI with the predictive recommendations. So in terms of interacting with this and getting started, build from what you're already doing, understand how the end user is going to interact with that interface. And then as well, like use cases are clearly going beyond just planning teams and engineering services with these systems. So that's it from us. And please feel free to come up and say hi to Javier and I. There's our contact information up there. And we're happy to talk about the digital twin frameworks in relation to this platform we've described today. Thank you.
Have Alireza to Akshay, sorry, to present.
Thank you. Sorry. Okay, good morning, everyone. Alireza Parhami with DC Water. Am I? Yeah. DC Water, I'm leading the implementation of digital twin on the collection system and water distribution side at DC Water. I'm here today with my colleagues at Bentley, Akshay Nirala and Paul West. He's, I guess, outside, to share with you the experience and the perspective that DC Water has gained over the implementation of digital twin on the distribution side. Lesson learned, couple of use cases or examples that have been successfully implemented as a part of phase one of this journey. And what's next, phase two, what's in our roadmap and what is in the works to take the digital twin implementation to the next phase. So, I'm sorry, forgot. Yeah. Okay, how the whole thing get started. DC Water Board of Director and senior leadership, they put together, develop a strategic plan, 5-year strategic plan, in which they charge all business units across the enterprise to look for opportunities wherever possible to leverage technology to bring enhanced, improved efficiency to the system, enhance customer experience, and essentially provide reliable drinking water in a safe, reliable, sustainable, and equitable fashion. So that was pretty much the main the driver of digital twin implementation across DC Water. And we do have other examples that my colleagues in the room, they can tell you all about it, but today we are focusing on the water distribution side. So just as a proof of concept, we identified 4 areas where to give ourselves essentially to touch different aspects of our strategic plan objective, and also give ourselves build some level of confidence as far as what the journey that we are about to start. So as such, we I guess the data integration, connecting data from various sources. This is what you hear throughout this conference. Was obviously a no-brainer. I mean, once you connect the data, you can look at the data and make more better informed decision. However, as far as DC Water and the utility, we want to prove to ourselves and to our colleagues that data integration would provide tangible values. So what we did as a first step, we want to prove that this data integration will give us a better insight on our distribution system across the board, across different business units. We democratize the data, make the data that was otherwise in silos or in with different business owners or business units available to everyone across the board. And I guess getting a better sense of our water distribution system performance, establishing the reliability or validating our understanding of our non-revenue water or water audit was one of the other objective, and also visualizing by simply visualizing the data that sits on the SCADA system. And essentially what we are doing here, the first three objective has not much to do with the hydraulic modeling, to be honest with you, just looking at the data that would have been otherwise probably either neglected or not fully utilized. So looking at the pump, for instance, pump performance, looking at the head discharge curves in real time over a long period of time. What value does it bring to a utility like DC Water? How would it impact our preventive maintenance, or how does it enable our operational crew to better and more optimize operate the system? And the last one, which essentially has some element of hydraulic modeling, the traditional hydraulic model are normally built, calibrated to a limited data set over a given period of time. What this data integration, one of the side benefits that brings to the hydraulic modeling side of things, is just to enable us to continuously monitor or first of all, build trust in the model outcome or model simulation results, and also track the performance of the output of the hydraulic model in contrast with the actual field collected data. So that's one of the, I guess, objectives that I guess personally I believe that's really impressive, because instead of just attempting or initiating a hydraulic model calibration on a set time interval like 5 years or whatever, so we can now strategically focus on hydraulic modeling, fire flow tests, or whatever that involves around hydraulic model improvement to a specific zone based on the data that we collect in the field and what the model would shows. Again, we are talking about the data integration. Hydraulic model consume all sorts of data, but as a starting point and in phase one, we attempted to bring in just a limited data set, starting with operational data or like a SCADA data. Obviously, hydraulic model and GIS, they were already there because our GIS, our hydraulic model is built off of our GIS inventory, and we have a seamless data update or update mechanism already in place. But the two components that was, I guess, added to the mix and makes it a digital twin or real-time hydraulic model is a SCADA and integration of the billing record or customer billing AMI system. And to do that soon, I personally realized that it's one thing to know the data reside in a database, but it's a different thing to make the data available to like a vendor-specific technology and meeting all our cybersecurity and all the security requirements that IT understandably I guess put in front of us. So to do so, we work extensively with our IT department specifically and our operations SCADA administrator to establish a replica of that data source, which is kind of it is within the DC Water stage firewall, but it is in a demilitarized zone or DMZ, and then through that we have to go through a number of iterations and processes to make the data kind of available, accessible to what you would see and all this calculation that would come out of the tool. The AMR data, I guess, was relatively easier. The data still needs to be sanitized. Some confidential information needs to be kind of scraped, but that was a relatively easy one. So at this stage, the hydraulic model that we have has the digital twin that we have at this stage has full integration of SCADA. I would say partially, not completely seamless on the AMI data, and that's for a reason that we can I can share with you later on. But looking at data sources, again, not all the data have the same fidelity. They do not come at the same because time step, and whether they come on like a millisecond resolution, whether it makes any hydraulic modeling sense, or can we make any get any use out of it. And so essentially, we kind of went through a discussion internally and with Bentley to identify what would be that sweet spot or the optimal practical time step data that we can potentially make good use of in the hydraulic model. Again, we talk about these use cases. I'm going to cover just the basic one. Essentially, once we get access to the the SCADA data, now we have flow in and out of each of our pressure zones. So establishing a trend, or they call it machine learning algorithm, whatever that might be, that is a automatic, I guess, product that comes out of looking at the time series data over extended period of time. But what we are doing, we are in real time. We are monitoring what is an expected system demand or system production, in this case, on a day-to-day basis. And an incident, main break, flushing, or you name it, would happen, and we are deviating from that otherwise expected behavior or the system performance. We can call out those situation, and as I said, our operations would be, I guess, not that they do this, wouldn't see this data, but now they are seeing it in the context of what would have been expected of the system at that point of time. Otherwise, that spike would be always visible to a SCADA and the operations. But now we are putting the two data source, I guess, in the context of time and what it should be expected. And at the same time, we are looking at how, if there are other anomalies in the system in terms of demand creeping up, or essentially trending upwards or downwards, that would normally doesn't happen. But so we can track the system performance in terms of informing our leak detection crew or leak detection activities to be more focused on a specific zone now that we have the access to the data for extended period of time. Now I'm going to hand it over to Akshay with Bentley. He's going to cover a couple of more use cases.
Thanks, Alireza. My name is Akshaya, and here the third use case we're looking at is displaying the real-time heartbeat network model, which really gives us the operator or whoever has access to the browser can see the entire network in real time, and they can, towards the bottom, you can see time scroll bar also. So you can go back in time as well as see what might happen an hour or a couple hours from now using hydraulic model. And this, on top of this heartbeat network model, operators can go and perform multiple hydraulic simulations, as well as engineers and others, such as pipe break. So if there's a real incident and they need to understand how I should handle, what are the valves I need to close, all those information they can operate. I have a short video just after this slide. We'll look into that. And other operational events also can be simulated just within the browser. For example, one pump is broken, that needs to be shut down, or entire system is out because of the power outage. Those can be handled within the software also. So let's take a look at a quick video about these use cases or the hydraulic. It will just play here. Bear with me. I cannot go back. All right, maybe technical difficulty, as we always see. So here's a video that actually shows how an operator is not playing for technical reasons. You select a pipe and it automatically isolates, shows what are the valves that has to be closed, and sometimes we know those valves are inoperable. So you can say, oh, this is inoperable, and it automatically detects the other valves that has to be closed in order to isolate that section. And once that section is isolated, we can push the buttons and it will simulate that pipe break, showing the customers that will be impacted because of that break. And those information are critical for the operators because sometimes we may have to send boil water alert. And just within the browser with simple clicks without really understanding all the hydraulics, an operator can simulate pipe break. Same way they can simulate pump shutdown, some of the valve operation in order to identify or sometimes even delineate a pressure zone. They can, within the browser, by pushing a couple of buttons and without really understanding all the technical difficulties of the hydraulic model, even an operator can simulate multiple hydraulic conditions and understand how they should react in the system. With that, for the rest of the slides, want to request Alireza to come back and share.
So we're running a little bit behind.
Oh, I'm behind. Okay. So just quickly covering some lesson learned, I guess. I mean, as I mentioned, the data integration and bringing data obviously is a challenge on its own, but SCADA specifically sensitivity around like cyber attack made it put it at the top of the list in terms of challenges and consideration. Um, Support from the senior leadership. Obviously, we had a strategic plan. We have a support from general manager, CEO, COO. However, my personal experience has been that would put us so much, get us so much buy-in, and the remaining and get a ultimate and full collaboration from the specific operational staff remains a task for the digital twin implementation champion within the organization to sit down with them. Sometimes the lack of, I guess, trust in the hydraulic model, the lack of prediction that comes out of the tool, black box, whatever they call it, is a challenge. And unless that hand holding and acknowledging the fact that essentially the whole process is harmless, they can continue doing the process the way the way they used to. However, at least give this tool an opportunity or a chance. Those are I guess my personal I guess story that I can share with you. Okay, we talk about phase one, phase two of the implementation. Everything to the left of the screen are the data integration that took place. AMI partially has been executed, not completely. However, in 2022 and 23, the integration with our work order management system and eliminating some of those false alarm or some of those spike in the system that I showed you in the previous slide could be due to a known system maintenance, should be to a known main break. So essentially, there is no need for triggering an alert to operations to act on something that they already know, or if there is a schedule flushing. So those integration with our CMMS, or in our case Maximo, is in the works. We have an expanded network of transient and pressure monitoring system, and that the integration of those data sources to our hydraulic model or to our digital twin is also in the works. And in terms of asset management, as I mentioned, all these asset performance metrics could be potentially fed into our asset management platform that would be otherwise not benefiting from all these activities and all these system performance data that we have available to us. With that, thank you very much. And if you have any question, I guess we can take it after the.
Yeah, we'll take it after all the
Yep.
presentations.
Okay.
Thank you, Alireza. Next, we'll have Luke to talk about the next case study here. Thank you, Luke.
Hi, I'm going to present a case study on a medium-sized water utility and how they developed a cost-effective digital water twin in a relatively short period of time, and how not looking or not worrying about hydraulic accuracy in the initial stages allowed us to be more agile and rapidly produce a digital twin that gained acceptance and kept momentum within the organization. So a little bit about the City of Waterloo. It's a mid-sized utility with about 137,000 customers, and it gets 100% of its water from a regional authority. And they only operate the linear assets after the wholesalers' tanks and pumps, which leads to an interesting scenario for them where they have no access to SCADA data and no ability to control the flow of water into their network. And actually very limited insights into actually what's happening within the networks as well. So to give them some level of insights, they maintain about 48 hydrant IoT devices that give them pressure, flow, leakage information. And they also didn't have any access to the wholesaler's hydraulic model either. And even if they did, they don't have the staff trained on its use. So the city wanted more than just a passive stream of data. They wanted actionable insights onto what their network was capable of, especially with their limited network controls that they had. And no surprise by everybody in this room, because we're talking about digital twins, the assumption was that maybe a digital twin could help them with this problem. So the city wanted a solution that was simple to use, low cost, and able to integrate with their existing data sources. The city ended up deciding to use Qatium and just pull together a small team to build a hydraulic model and develop a proof of concept. Now, this would traditionally be a long, drawn-out process if you're trying to build a hydraulic model from scratch, but we knew that this was more about trying to get acceptance within the organization that a digital twin was going to work. So we weren't too concerned about how accurate the model was, but more exactly what it could do, and if we could connect it to a live stream of data. Within Qatium itself, there is the ability to build a hydraulic model. We have a little digital assistant. You'll see her on the right-hand side there, Q. Some people associate her with Clippy of the 90s, but we hope she is a little bit more useful than that. So we actually use this simple model that we built just from their GIS information as the basis for their digital twin, and then we connected that up with their live data streams. Obviously, connecting live data streams is another source of pain for many people who've done integration. So instead of going through the traditional process of firewalls and DMZs, we took a 1 month snapshot of data and created a stream of data that's flowing into Qatium through a loop. So it looked like it was live data, but it was just the same 1 month period floating over and over and over again, sort of like Groundhog Day in Qatium. This helped the city of Waterloo better understand what the solution was by looking at a proof of concept with their own data sources, and understand the potential of what could be done. And this at this approach, we could then we gained acceptance. We showed it to a few different people, and the abilities of the digital twin became apparent. So they decided that they would approach the wholesaler and ask for the digital twin so we could further upgrade the model and move it forward. So that's exactly what we did next. We took the region's wholesale planning model and decided to move that in. So we're taking small steps to improve the digital twin one by one. We're obviously not interested in the full service area, so we did things like cut it down to a small area, change it from a maximum day worst case scenario to average day, and connected in that historic live data stream and pushed it into the digital twin platforms that you can see on the right-hand side there. We connected into that little loop of historic data, and we were already seeing accuracies between 80 and 90%, so we had quite a bit of confidence that this was working correctly. We did some further improvements of the digital twin. My video is also not playing, so heads up for anyone who has videos, prepare yourself for that. We included valves and hydrants in the model so that we wanted this to be used by operators, so we wanted them to have the exact same controls and abilities the way to work with the network that they were used to. We also went through the process of connecting the live data stream, so we had the continuous feed of live data confirming that the model was working correctly. At this point, we were very comfortable that we extended out the digital twin to more people, so the operational groups, and held some workshops to understand where potentially could this be used. And I'm sure this list comes to very little surprise to most people. These are probably the ones that are discussed most often for water distribution digital twins. The big ones there are the ones that highlighted were the ones that the city thought had the most potential. So fire flow capacities, water main shutdowns, unidirectional flushing, and water quality modeling. water main shutdowns are interesting because we're hearing similar things in the DC case study as well. I'm just going to talk about some next steps as well. So integrating more and more data is going to be important. Like I said, we're trying to take small steps to become quite a large project. So taking in that regional SCADA data and those AMI customer data to improve the digital twin, keep getting that accuracy up. And then we really think getting those sources will improve the quality of the flow information there. And we're going to conduct data-driven trials. So we're going to provide it to a mix of office-based users and field-based users, and then look at the efficiency. So, we'll do the task the old way and time them and see how long it takes, and then the new way, and see does it actually improve any efficiency using the digital twin, because we want to have that quantifiable proof that not only to expand it locally, but be able to share with other small to medium utilities that there is a path forward for them to have a digital twin. And we also expect the application to be easy to use. So we're going to split it into two cohorts. One cohort where they'll have the traditional training, sit down in class, explain how everything goes. And the other half is going to be totally self-guided. They're going to have the application, maybe a little bit of guidance on what they can do, but they'll have to figure it out for themselves. And we'll see which one performs better, and maybe there's a mixture between, but we think that, that this is a simple solution and it should work. And I'll just quickly end on saying that it shouldn't matter if your project is really big or small. Taking small steps and accepting that maybe some things won't be as accurate temporarily and that they can be fixed later will help you on your digital twinning now. So I hear many utilities say, oh, this is really great, but I've got so much more to do that I can't get there, and maybe I'll talk in 2 or 3 years. But you can break this down into small steps and get to your end goal much sooner, maintain momentum, and get acceptance in your digital twin. There's no point waiting 3 years, doing a big launch, and then it falling flat because you missed out on some simple assumption. So on that, I will say the last thing we should also consider is that this sharing of information helps make sure everyone moves forward and understands and paves the way forward to others in the future. And that's, I can't wait to hear the rest of the talks. So thank you very much.
All right, thank you. I appreciate the opportunity to come speak. I'll maybe talk kind of fast, make sure we get some time for some discussion. I'm going to give a pretty broad overview of how we at Veolia have worked with the city of Milan and their largest wastewater treatment facility to implement digital twin technology. I'm our service programs manager in the U.S. I'm in Cary, North Carolina. I'm a biological process guy. That's my background for 20 plus years. And I've really started getting involved in the digital side of things in about the last 3 years or so. And I'm a very firm believer in the value and the outcomes that we can achieve by bringing digital twins into our wastewater treatment plants. I also want to just say a quick thank you to the folks who've really done all the work on this, our Kruger Denmark team, who are the keepers and developers of Veolia's digital twin technology, the operations group at the Niceto wastewater plant in Milan, and the Veolia Water Technologies Italy team, who really implemented this in conjunction with those other organizations. Real quick, Niceto is the largest wastewater treatment facility for the city of Milan. It is operated by and nearly all of its effluent goes to reuse. So they really are the largest provider of reuse water from a single treatment plant in Europe. Lots of agricultural and other reuse uses out in the surrounding countryside. The capacity of the treatment facility is 1.25 million population equivalents. I don't know exactly what flow that is. Depends on what kind of conversion factor you want to use for that. But it's a quite large activated sludge wastewater treatment facility. Now, they had lots of the same kind of drivers that you might think of with a wastewater treatment facility as to, where they saw room for improvement, things that they needed to do at their plant, from just maintaining more stable and reliable effluent, so the quality of the reuse water that they were delivering was consistent, to saving energy, saving chemical, all those, normal kind of drivers. This project really got started in defining those drivers specific for them. I want to say around 2015. And in talking with Veolia, we began to identify those drivers and identify the types of features that we could bring to them to achieve these goals that they had. Now, to address that, Veolia's platform is called Hubgrade. That's a very broad a brand name for our entire suite of digital technologies. The digital twin portion of that is Hubgrade Performance Plant. And that is, it has modular building blocks based on different unit processes. So there's a building block that's specific to DO and nitrogen control, a building block for chemical control. And we'll see a bit more of that in just a second. One feature of this technology is we deliver this 100% through the cloud. We establish an OPC server and bridge on site, and that handles the communication from the plant network and the PLCs controlling the different unit operations. All the algorithms, everything is housed off-site, and it's all delivered through the cloud. And so with the digital twin, the way we apply it, so we're obviously getting all the data. We use about 2 years worth of historical data to really kind of fine tune the algorithms that we're employing. Those algorithms we employ have been, we've been working on these for 20 plus years. The Kruger Denmark team really started with some simple model predictive control back in the very early 2000s, and it has grown from there to a suite of over 60 different features that target specific unit operations. And one thing that is kind of unique, we're not only gathering insights from that and using the model predictions to give insights to the operators, we're actively controlling all the aspects of the system. So every 2 minutes, implementing a new DO set point, a new flow set point for a particular pump. So we're actively fully controlling the facility and essentially putting it on autopilot. At the Naceto facility, I said this really discussion started back in 2015. Contract was entered into in 2018, and then it was implemented over that time frame. They also worked with a local university to evaluate the expected returns and confirm that they had some other voices telling them that yes, this is viable. You can achieve the outcomes that you want to achieve. It was ultimately fully deployed in 2019 and incorporated 11 different features to control the treatment facility. I won't mention all of these, but all these different unit operations. So the way we've approached this over the last 20 years is targeting basically a digital twin in each of these areas. And you can implement just one in a facility. You can implement 2, 3. You can implement 11. And the more you implement, the more you're basically building a complete model of the facility as opposed to just a single unit operation or two. And the more you put these building blocks into a facility, the more the overall facility is going to be optimized. So with that, I mentioned it's been in operation since 2019. In that time, since it was implemented, they've achieved a 25% reduction in their energy consumption at the treatment plant. They used to use quite a lot of chemical for phosphorus precipitation. That has dropped by 68% because we're able to utilize the digital twin to control the reactor environments and really enhance the biological phosphorus removal. Altogether, the equivalent carbon CO2 emissions have dropped by 1,200 tons. So a significant outcome there. And with those various operations at the plant being optimized, we've reduced the chemical sludge generated by the facility by 116 tons of total solids a year. So they've achieved some great outcomes. In the future, things that we're working on with our digital twin technology are implementing more AI to in real time retune the algorithms that are used and actually update and change those algorithms over time to try and squeeze a little bit more savings and keep that digital twin operating in top fashion. So thank you. I appreciate it. And
Thank you, everyone. So we got 6 minutes for questions or comments. Oh, here.
Pedersen from VCS Denmark. I heard 4 examples of really nice digital twin platforms that you presented. how do you think in the future that these platforms can collaborate so that I can have a feature for one of the platforms and also from one of the other platforms?
Thank you.
I believe that question is a question for technology vendors. I guess as a utility, we are just, we are, for the time being, we are limited to what Bentley has to offer. And we built our platform with the hydraulic model that we already had in Water Gems, which is also a Bentley product. So we were limited in our choices without sacrificing the data resolution and all these components that is already programmed into our functioning hydraulic model. So that was, I guess I shouldn't say the only, but that was the main criteria to entertain water side or digital twin service offering by Bentley. I am not quite sure how the technology vendors, they seamlessly, they are willing to collaborate, but I know once the data is distilled and consumed or aggregated and is used, presented to one of these data, like a digital twin systems, should be technically should not be any technical problem. Data exchange across uh, systems. So that's my humble, I guess.
Yeah, I'll just add to that. First, my hope would be in time, Veolia will be able to provide all your needs and address all of these. But I know that's not realistic. I think you have to take small steps, and I think that was mentioned earlier. And the first step in that, I think, is ensuring that at least the data can be shared. I don't know how you get to a point where as a utility, you're not going to be dealing with 19 different entities to try to implement digital twin technology in several of your different systems. But there is certainly room to collaborate and make it easy to share data that multiple entities need.
I would agree, and I think it links back nicely to the opening talk by Neom. You have lots of different vendors working together, and we should, as an industry, force interactions between them, right? And I think even the digital twins here with three or four different systems, and there's no reason why they can't interact from source, all the way from source to treatment. And I think that's, as an industry, something you just have to push and not be dictated by the vendors, even though I'm sitting up here as a vendor myself.
I think you guys have covered it. This one? Yeah, it's been covered really well. Interoperability will be a word more and more used as well. Because these models are in the cloud now, there's no reason we can't run them in parallel. And then for a particular use case, to see how these models run against the other, to see which one's performing best for a particular use case type of thing. And you can always just take their models and just bring them into Info 360 as well. So.
Well, I'm going to close with a utility perspective here. So I think it's true that the interoperability is a big part. And what I see is a utility is to play a role to facilitate the discussion with all the vendors together. Because we have a Microsoft, we have an Innovyze product here, and we have an S3 product. So it's how do we bring all the systems together and having them to talk with each other, whether it's APIs, whether it's internally developing some code or things. So I think it's a great question we need to explore further. We got 2 minutes left. We probably have one more question if anyone have other thoughts or questions. Oh, here.
Yes. So in the discussion from DC Water about data collection frequency, could you discuss how you feel that utilities that are using AMR or any sort of water metering sort of situation that's not AMI can benefit from developing digital twins, and how they can be implemented without having that frequency of data that we'd all like to have?
I guess having the frequency of data transmit is one thing. Having the local or on-site data collection resolution is one thing. The data could be collected in absence of AMI, AMR at the end of the month using the traditional way that it used to be probably collected anyway. But whether that data could be recorded at source to the extent that that pattern or that like time variation over the span of time could be established. Once that component has been addressed, I believe the digital twin, we talk about machine learning, pattern, I guess, or extrapolation of data into the future is something that can be done even in static or disconnected data dump of consumption in this case, or billing information. Um, but I do not know if digital twin does not have that connectivity with the actual consumption at all, or has one value for the entire month. The remaining would become kind of a guess game. We cannot incorporate, or we lose the value that real time pump or basically production data would provide if we are missing that comparable in time a spread of the demand or consumption. So I don't know whether I answered your question, but that's all I can say.
Sure, I'll just quickly add that going back to my presentation, I was trying to push the point that just because you don't have all the data now doesn't mean you can't get some type of insights. And your AMI, AMR will provide you really high density resolution of information, but it's not always necessary for a digital twin. If you can do a flow balance, you're probably going to be able to get accurate pressures within like 90% of your areas. And instead of focusing on how do I roll out hundreds of AMR or AMI meters and get that in, you could potentially just connect in a few large meter customers that probably have higher impact on your network first, and then worry about the AMR, AMI piece later.
Thank you so much. With that, I'd like to conclude the session, and let's give the round of applause for our panelists.